Hello, and welcome to a quick presentation on libre-soc and microwatt. Um, libre-soc and microwatt are power ISA cores. The difference there is everybody thinks that the IBM is the only company that makes power compliant processors, so they keep calling it the Power 9 instruction set and the Power 10 instruction set. That's like calling the x86 instruction the Pentium 3. Both libre-soc and microwatt are Power ISA 3.0 compatible. That's what they're aiming for. Which the IBM Power 10 processor happens to implement much more than that. It's got compatibility modes and things for going back for Power 8 and Power 7 and so on. It's quite interesting processor. So these are entirely Libre licensed code. So the microwatt is Creative Commons. Both projects have been written by software engineers, so use testing, continuous integration in the case of microwatt, but they have unit tests and etc. etc. So the microwatts in VHDL, you can simulate it. I'll show you that in a minute. The libre-soc one, here's it's a big website. We've got a whole stack of repositories. It's broken down to different areas, but we also use microwatt compatibility for testing. Right. Before I get into that, I just wanted to show you some quick pretty diagrams, shall we say. So this is a basic layout of the interfaces. We're currently running a finite state machine similar to Pico RV32, where it's one instruction every 7 to 10 clock cycles. It's good enough. It was quick and dirty. It got the job done. But underneath there are pipelines that ultimately will be able to create a superscalar architecture from. Now, it's a wishbone arbiter, which goes over to a wishbone master, a DMI interface, and we also had a JTAG boundary scan in, and there's a single interrupt line in it as that goes in as well, right? And that's quite important because when it came to the to doing the debugging, I had to put in, I had to basically, you're running instructions, you've got no idea whether, in amongst 10,000, or in the case of the simulations, I was doing 15 million instructions, you have absolutely no idea which one is wrong or why. And so if what we could do was single step through a microwatt core and get a printout, a debug dump. Here we go, debug dump here of the program counter, the machine status register, condition register, the XER exception register, and the special purpose registers, and also the general purpose registers. Then, if you can single step, which is what this is doing, it's a debug memory interface. So it's a DMI request. The specification is it's a de facto standard specification that both microwatt and libre-soc comply to. If you can do that, then you can get basically a running stack dump of every single register and thing. And then if you can do the same thing with the other processor, and that's this DMI interface here. If you can do exactly the same thing with that other processor, then you can do a diff -u on the two files, right? So that's what I did. And in that way, rather than messing about going, I've got 10,000 instructions, I don't know which one it is, you just do a diff, and oh look, it's that one. That one produced a register that's wrong, and which was really useful. And I say useful, absolutely essential. Now, The next critical thing that I did after sorting out the basic core was I went, okay, I need to do Verilator simulations, and so what I did was I actually modified the microwatt source code to drop in what I call an external core, right? And again, coming back to that diagram, right, it's basically the wishbone master interface, the DMI interface, the interrupt line. Oh yeah, it's this lot: instruction wishbone, data wishbone, interrupts, and DMI. That's the debug memory interface, right? And treated that as an external core to as far as Verilator is concerned. It's just in Verilog. So here's the DMI debug memory interface address, data in, data out, request, write, acknowledge. There's the external interrupt line. And here's the wishbone instruction, data in and data out, and there's some useful debug stuff. Right, now there should also be in here. Where is it? It's part of this file, UART0. This is a mini sock fabric that's built into, been written by the microwatt team, and you can have a UART, a ZIX interface, which is interrupt controller. There's a UART, at address C000. So it was critically important to be able to be compatible with these, so that we could actually run exactly the same program. So we don't have to mess about going, oh well, I'll reinvent the wheel. No, just drop the libre-soc core into microwatt as a direct compatible replacement for the microwatt core. So let me lower that and lower that out. Let me flip over to the other one here, the other screen here. So ls Verilator /microwatt Verilator.cpp. So here is where in Verilator you got a simulation loop going around. I put in memory dumping so that we can take snapshots of memory, analyze it in the middle if we needed to. It also outputs those GTK wave files. These ones, these are monsters, but it's absolutely essential. There's 10,000 signal traces in this, but it turned out to be absolutely essential to have access to them, which is why I've concentrated on making sure that we've got the simulation. So I added in a block RAM simulator. And the existing thing, there's the reset. If it starts up the reset, do set the external reset to 0, do a single 5 clock cycles of tick, and then set the change the reset. This is the main while loop. While it's not got finished, there's a tick, there's a save. Where's the UART? Where's the UART? UART. Oh, there it is. There's everything. There's your UART transmit and receive signals, and that's just a serial line, serial console. But what the microwatt team did was they put an emulator of a 15200 serial console. So microwatt Verilator /hello world /hello world.bin. Woohoo! And that's running a simulation in the thing. Now let's do the same thing here. /microwatt /hello world.bin. And it does the exact same thing. Notice the difference in the speed. Huh? That's because one of those is a libre-soc core, and the other one is microwatt. And you can see earlier I ran some things. Now it's outputting a whole stack of snapshots, and that I can have a look, and go back, run things again. We can actually run Linux, but it takes 60 hours to complete at 5,000 instructions a second. It's mental. But so that's a little bit too slow. That is. So instead, what we'll do is we have the FPGA version. History. Build ctrl build .libre-soc hello world, and this should just work. And on here, oh hey! Now you notice how quick that was over there. How much faster that was. That's the FPGA version running on a Versa ECP5. Anyway, all the same thing, all the same HDL, one simulated, one thing, but doing the comparison was, I think, was critically important. So, thank you very much.